Let's start with the simplest object in all of machine learning, a straight line. It takes a number in, multiplies it, adds a little, and hands you a number back. For the next few minutes, I want you to think of a neural network as nothing more than a machine for bending lines like this one. Here is the whole tension of the field in one picture. A straight line can only do so much. It can steepen, it can flatten, it can slide up or down, but it can never curve, and the world we want to model is full of curves. So the plan for this video is simple. First, we'll see exactly why stacking straight lines keeps giving us straight lines. Then we'll introduce the ingredient that breaks the spell, the activation function, and watch a flat line suddenly fold into a curve. Let's build the trap first. Imagine a layer of our network. All it really does is take the input, scale it, and shift it. On our axes, that is just a line with some slope and some height. Now stack a second layer on top. It takes whatever the first layer produced and applies its own scale and shift. Surely 2 layers can do more than one. Let's actually watch what happens when we compose them. I'll feed the output of the first line into the second, point by point. Watch the composed result forming on a fresh set of axes as I sweep across the inputs. And there it is. The composition of 2 lines is just another line. A different slope, a different height, but still perfectly straight. No matter how cleverly we chose the 2 layers, the fold we hoped for never appeared. Let's push it further to make the point undeniable. I'll add a third layer, a fourth, a fifth. 10 linear layers deep, a genuinely deep network. Watch the whole tower. Now I'll collapse the tower. Every pair of stacked lines merges into a single equivalent line, over and over, until the entire 10-layer network flattens into one. All that depth bought us absolutely nothing. This is the collapse theorem in visual form. A network built from pure linear layers, however deep, is mathematically identical to a single line. Depth without curvature is an illusion. To escape, we have to bend something on purpose. So here is the fix, and it is almost embarrassingly small. Between 2 linear layers, we insert one little function that is not straight, just one bend. That's the activation function, and it changes everything. Let me show you the effect immediately, before any formulas. Here is our flat composed line again. Now I'll switch on the nonlinearity between the layers and let you watch the line respond. There, the line folds. A crease appears where there was none, and suddenly the network can trace shapes a single line never could. That fold is the entire reason activation functions exist. Everything else is a discussion of how gently or sharply to bend. So let's meet the family of benders, one at a time, all drawn on the same axes so we can compare them honestly. We'll start from the one that does nothing at all and work toward the ones that do a lot. First, the identity. It's the do-nothing activation, the straight diagonal line we began with. Whatever comes in goes straight out, unchanged. Its job here is to be the baseline, the shape we're trying to improve on. Now watch the slope of the identity as I run a dot along it. The steepness never changes, it's the same everywhere, left to right. Hold that idea of slope in your mind because slope is the secret hero of this whole story. Here comes our first real bend, the sigmoid. Picture taking that straight line and gently squashing both ends until they flatten out. Big negative inputs get pressed down toward the floor. Big positive inputs get pressed up toward the ceiling. The sigmoid lives entirely between 0 and 1, which is why people love it for turning a raw score into something that feels like a probability. In the middle it rises briskly, but out at the edges it goes almost perfectly flat. Now here's the part that matters for learning. Run the slope gauge along the sigmoid. In the center the slope is healthy and strong, but out in the flat tails the slope shrinks toward nothing. Why care about slope? Because when a network learns, it passes a correction signal backward through every layer, and that signal gets multiplied by each activation's slope. Where the slope is near 0, the signal nearly vanishes. That's the famous vanishing gradient, and the sigmoid's flat tails are guilty of it. Let's fix one small annoyance. The sigmoid is stuck between 0 and 1, so its output is never negative and it isn't centered on 0. Its cousin, the tanh, keeps the same gentle S-shape but stretches the range to run from -1 to +1. Being centered on 0 is genuinely helpful. It means the activation can push a value negative as easily as positive, which tends to keep the signals flowing through the network balanced rather than drifting to one side. But run the slope gauge again and you'll see the same old problem. Tanh is steeper than sigmoid in the middle, which is nice, yet the tails still flatten out. Push far enough in either direction, and the gradient once again fades away. So both of our smooth S-curves share a weakness. They saturate. Out at the extremes they go flat, they stop responding, and they starve the learning signal. This is exactly the frustration that pushed people toward a completely different shape. Enter the rectified linear unit, or ReLU, the workhorse of modern deep learning. Its idea is almost brutally simple. If the input is negative, output a flat 0. If the input is positive, just pass it straight through, unchanged. Notice it isn't a smooth curve at all. It's two straight pieces meeting at a sharp hinge at the origin. That single kink is the entire nonlinearity. It turns out one sharp corner is enough to break the collapse we saw earlier. Now the slope story gets refreshingly clean. On the positive side, the slope is exactly 1, so the backward signal passes through completely untouched, no shrinking at all. That's why deep networks with ReLU train so much more easily. But look at the negative side. There the function is dead flat, so its slope is exactly 0. Any signal trying to flow back through that region is multiplied by 0 and simply disappears. The neuron passes nothing. This creates a real hazard called the dying ReLU. If a neuron gets stuck always receiving negative inputs, it sits forever on that flat side, its gradient is always 0, and it can never update. It's effectively dead weight in the network. So people made a tiny clever repair. Instead of a perfectly flat negative side, give it a very gentle downward tilt. That's the leaky ReLU. Positive inputs still pass straight through, but negative inputs leak through with a small slope instead of dying at 0. The tilt looks almost too small to matter, but its whole purpose is the slope. Run the gauge along the negative side now, and it reads a small number instead of 0. A small gradient is a living gradient, so the neuron can always crawl back to life. Let's line up what we have so far, all on the same axes. Sigmoid and tanh, smooth but saturating. ReLU, sharp and efficient but with a dead side. Leaky ReLU, the same idea with a safety leak. Each one is a different answer to a single question: how should the slope behave? Now some people find ReLU's sharp corner a little crude. Nature rarely bends at a perfect right angle. What if we could keep ReLU's wonderful efficiency but round off that harsh hinge into something smooth? That leads us to two elegant curves. The first is Softplus. Think of it as ReLU that has been gently ironed smooth. Far to the right it hugs the same straight ramp as ReLU, and far to the left it eases softly down toward 0. But it never has a sharp corner anywhere. Because Softplus is smooth everywhere, its slope changes gradually instead of jumping. Run the gauge across it and the slope glides from nearly 0 on the left up toward 1 on the right, passing through every value in between. No sudden cliffs. And here is a lovely secret. The slope of Softplus is exactly the sigmoid we met earlier. The gentle S-curve that gave us so much trouble as an output function turns out to be the perfect smooth switch controlling how much of the signal Softplus lets through. The second smooth cousin is GELU, the activation quietly powering most of today's large language models. It looks almost exactly like ReLU, with one delicious twist near the origin. Watch the region just left of 0. See that little dip? Just below 0, GELU actually dips slightly negative before curving back up, then rejoins ReLU's ramp on the right. Instead of a hard on or off switch, GELU softly and probabilistically decides how much of each input to let pass. That dip gives GELU an unusual slope signature. Run the gauge and you'll see the slope actually go a touch negative in the dip, then climb smoothly back up to 1 on the right. It's a richer, more expressive bend than the plain ReLU hinge. Now let's do something satisfying. Let's morph through the entire family on one set of axes, watching a single curve continuously transform, from identity to sigmoid to tanh to ReLU to leaky ReLU to Softplus to GELU and back. As it morphs, keep your eye only on the slope, That is the real character of each function. Flat means a fading gradient, steep means a strong one. A corner means an abrupt switch, a smooth bend means a gentle handoff. The shape you see forward is exactly the gradient the function sends backward. Let's make that forward and backward link concrete because it's the heart of the whole video. When a network learns, it sends a correction backward, and at each activation that correction is simply multiplied by the local slope. So the slope you can read off the graph is literally the learning signal's fate. That reframes every choice we made. Sigmoid and tanh strangle the signal at their flat tails. ReLU passes it perfectly on one side and kills it on the other. Leaky ReLU keeps a trickle alive. Softplus and GELU hand the signal off smoothly with no cliffs. Same picture forward and backward. Now let's return to the promise from the very beginning and actually build a curve. I'll take a few ReLU pieces, each a simple bent line, and add them together with different heights and hinge positions. Watch what happens as I add them. Each hinge contributes one crease, and as the creases stack up, the flat line grows into a jagged shape that hugs a real target curve. This is a network learning, in miniature, right in front of you. This is the deep secret the collapse theorem was hiding. Lines alone stay lines forever, but lines plus even one humble bend, repeated across many neurons, can be stitched into essentially any shape you want. Depth finally means something. So how do you choose among them in practice? A simple rule of thumb. Reach for ReLU or one of its smooth cousins, GELU and Softplus, in the hidden layers where you want strong, non-vanishing gradients. Save Sigmoid and tanh for the output, where you actually want that squashing into a bounded range. Step back and the whole subject fits in a sentence. An activation function is just a chosen way to bend a straight line, and the way it bends is the same as the way it passes learning backward. Master the slope and you understand the function. That's the tour. Now every activation you meet is just another curve bending a line. If this made it click, subscribe for more visual math.